Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
My Weird Prompts is an AI-generated podcast produced by Daniel Rosehill, a verified human with documentation to prove it. While every effort is made to ensure our AI hosts draw from credible sources and run on cutting-edge models, they do occasionally make things up with alarming confidence. As with everything in life, and especially this podcast, treat all claims as spurious until confirmed to be not. Daniel, Herman and Korn accept no responsibility for any decisions made based on the confident ramblings of our artificial presenters. Now, today's episode.
Hello there, Herman and Korn. So, as you know, we like to get into the technical depth of generative AI and all things AI in this podcast. I thought I'd ask today about one of the more challenging forms of generative AI, and that is video generation. So we can be talking about a few different modalities. One of those is text to video, in which the user writes a prompt and generates a video. And the other form is image to video. And there's two forms that you see a lot of. One is start and end frame, so frame interpolation. And then we can have, different models of different implementations. Some just with a start frame, some even with a reference video. So there's a lot of diversity within this modality. But of all the forms of generative AI, when I began looking at what I could do locally on my own computer, video is really tough, and video is the most expensive because it's the most computationally demanding. So when we're talking about video, really fundamentally what video is, a sequence of images at whatever the frame rate is, 24 FPS or 30 FPS. So it kind of made sense when I thought about it like that we might be asking in an image generation to generate one image, but when you're asking an AI tool to generate a video, you're asking for it to generate a stream of images. That makes sense, that the motion is going to be preserved. So I'd like to talk about the various ways that AI models do this and how we might be able to get from where maybe we are now to a form of video generation model that is always going to be very challenging to run on local inference for, let's say, GPUs in the sub 24 gigabyte VRAM category? Or are there some ways that we can potentially run this type of generation on more modest hardware?
Welcome back to My Weird Prompts, the podcast where we dive deep into the strange and fascinating questions our producer Daniel Rosehill sends our way. I'm Korn, and I'm joined as always by my co-host Herman Poppleberry. Today we're tackling something that's been on a lot of people's minds lately, video generation AI. And not just the flashy stuff you see on social media, but the real technical nitty-gritty of how these models work, and whether regular people can actually run them at home.
Yeah, and I think what makes this prompt so interesting is that it cuts right to the heart of a fundamental problem in AI right now. Everyone's excited about text-to-video and image-to-video models, but almost nobody's talking about the computational wall you hit when you try to actually use them. It's a really important gap in the conversation.
Exactly. I mean, when you think about it, video generation sounds like it should just be a natural extension of image generation, right? You're just making a bunch of pictures in a row. But apparently, it's way more complicated than that.
Well, hold on. It's more complicated, but not for the reason you might think. Let me break this down because I think Daniel's framing in the prompt is actually really helpful here. At its core, video is indeed just a sequence of images. When you're watching something at 24 frames per second, you're literally watching 24 individual images play back really quickly. So conceptually, yes, generating video is about generating multiple images in sequence.
Right, so why is it so much harder computationally? Like, if I can generate one image with a decent GPU, shouldn't I just need, a bit more power to generate 30 of them?
Aha! And that's where you're oversimplifying it. It's not just about doing the work 30 times over. The real challenge is temporal coherence, making sure the motion looks natural and consistent across frames. You can't just independently generate 30 random images and expect them to flow together smoothly. That would look like complete garbage, honestly.
Okay. So the AI has to think about how things move between frames.
Exactly. And that's computationally expensive in ways that static image generation isn't. When you're generating a single image, you're working in what we call the image space. But for video, you need to maintain consistency across temporal dimensions. The model has to track objects, predict how they'll move, maintain lighting and shadows as things shift around. It's exponentially more complex.
So that's why we're looking at these different approaches, like text to video versus image to video, or frame interpolation.
Precisely. Different approaches are trying to solve this problem in different ways. Text to video is the most ambitious. You give it a description, and it has to generate the entire video from scratch, maintaining coherence across all those frames while also matching your text description. That's computationally brutal.
And image to video is easier.
Somewhat, yes. When you give the model a starting frame, or even better, a starting and ending frame, you're constraining the problem. The model doesn't have to imagine everything from nothing. It knows where things start and where they end up, so it's basically doing intelligent interpolation. That's less demanding, but still pretty heavy.
But here's what I'm still confused about. We have decent consumer GPUs now, right? Like, 24 gigabytes of VRAM isn't pocket change, but it's not impossibly expensive either. Why can't we just run these models locally?
Because the computational demand isn't just about memory. It's about the sheer number of operations required. Video generation models need to process information across both spatial dimensions, width and height, and temporal dimensions, time. That's 3 axes of complexity instead of 2. And then you layer on top of that the fact that these models are using techniques like diffusion, which require multiple denoising steps.
Wait, multiple steps? So it's not just generating the video once?
No, not at all. Current state-of-the-art models, especially the diffusion-based ones, work iteratively. They start with noise and gradually refine it over many, many steps. For a single image, that might be 50 steps. For a video with 30 frames, you're looking at potentially 50 steps per frame or more. You can see how quickly that explodes.
Okay, so that's the core problem. But the prompt is really asking, is there a way to make this more efficient? Can we get video generation working on more modest hardware?
That's the million-dollar question, and honestly, there's real research happening on this right now. The short answer is maybe, but it requires some clever engineering. There are several approaches being explored. One is what researchers call temporal distillation, basically training smaller, more efficient models by having them learn from larger models. You're compressing the knowledge.
So like, you take a big expensive model and teach a smaller model to do the same thing?
In a sense, yes. The smaller model learns to mimic the behavior of the larger model, but more efficiently. It's not perfect, you lose some quality, but you gain a lot in terms of computational demand.
And that actually works? You don't lose too much?
It depends on the implementation, but current research suggests you can get pretty reasonable results. The trade-off is usually in video length or resolution. You might generate shorter clips or lower resolution video, but the motion coherence can still be quite good.
Let's take a quick break from our sponsors.
Are you tired of your graphics card collecting dust? Introducing Vito Max Accelerator Crystals, the revolutionary mineral-based performance enhancers that you simply place near your GPU. These specially aligned quartz formations have been shown to increase rendering speed through proprietary resonance technology. Simply position them within 6 inches of your graphics card and watch as your video generation times mysteriously improve. Users report faster processing, cooler temperatures, and an inexplicable sense of well-being in their office spaces. Vito Max Accelerator Crystals, because your hardware deserves a little boost from nature. Each set includes 13 mystical stones and a velvet pouch. VUI now.
All right, thanks, Larry. Anyway, back to the actual technical solutions here. Another approach that's getting a lot of attention is what we call latent space compression. Instead of working with full-resolution video frames, the model works in a compressed latent representation.
Okay, now you're losing me. What's latent space?
Right, sorry. So imagine you have all the information in a video, every pixel, every color value. That's a huge amount of data, but most of that data is redundant. A latent space is a compressed representation where you only keep the essential information. It's like, imagine describing a video to someone instead of showing them the video. You don't need to describe every single pixel, just the important stuff.
So the model generates in this compressed space, and then you decompress it at the end.
Exactly. And because you're working with less data, the computational demand drops significantly. This is actually what a lot of current models are doing. The challenge is that compression always loses information, so there's a quality trade-off. But it's a very practical trade-off for getting things to run on consumer hardware.
How much of a quality hit are we talking about?
It varies, but with good implementations, you can maintain pretty high visual quality while getting substantial speedups. We're talking maybe a 10 to 20% quality reduction for a 2 to 3 times speedup in some cases. That's a reasonable trade-off for a lot of use cases.
So if someone has a 24GB GPU, which, let's be honest, is what a lot of people who are serious about local AI have, what can they actually run right now in 2024?
Well, smaller models, definitely. There are emerging models that are specifically designed to be efficient. Some of the research coming out of academic labs shows that you can run reasonably good video generation with 12 to 24 gigabytes if you're smart about it. You might be limited to shorter clips, maybe 5 to 10 seconds, or lower resolutions, like 480p or 720p instead of 1080p. But the results are getting quite good.
Wait, but I thought you said the bigger models need more VRAM?
They do. The really large models, and we're talking about some of the frontier models that are getting all the press, those often need 30 plus gigabytes or even higher. But there's a whole ecosystem of smaller models that are being developed specifically for efficiency. It's like, imagine the difference between a sports car and a sensible sedan. The sports car is faster and flashier, but the sedan gets you where you need to go and is way more practical.
Okay, so the landscape is actually more nuanced than you can't run video generation locally. There are options, but they're not the same as what you'd get from a cloud service.
Exactly. And I think that's an important distinction. If you go to Runway or something like that, you're getting high quality, long form video generation because they have massive server farms. But if you want to run things locally, you have to make different choices. And those choices are getting better all the time.
So, what about the different modalities Daniel mentioned? Text to video versus image to video? Is one significantly easier to run locally?
Image to video is generally easier, and frame interpolation is even easier than that. Here's why. With frame interpolation, you're literally just filling in the frames between two existing frames. That's a constrained problem. You know what the start and end should look like, so the model just has to figure out the smooth transition. It's much less open-ended than text to video.
So if I wanted to run something locally and I had limited resources, I should start with frame interpolation?
Absolutely. That's the most practical entry point. You can take existing video or images and create smooth, slow motion effects or enhance frame rates. It's genuinely useful, and it's the least demanding computationally. Then, if you want to level up, you could try image to video with a start frame and an end frame. That's more demanding but still manageable on consumer hardware with the right model.
And text to video is the hardest.
By far. You're starting from nothing but a text description and generating an entire coherent video. That's the most ambitious ask, and it's why those models tend to be the biggest and most demanding.
Let me push back on something though. You keep talking about efficiency gains and optimization techniques, but aren't we still fundamentally limited by the laws of physics here? I mean, if generating a video is inherently more computationally expensive than generating an image, can we really engineer our way around that?
That's a fair challenge, and you're right that there are hard limits. You can't generate something from nothing without expending computational resources. But here's the thing. Efficiency isn't about breaking physics. It's about being smarter about the computation you're doing. Right now, a lot of these models are using brute force approaches because they have access to massive compute resources. But if you have to be more clever, you can get surprising results.
Give me an example.
Okay, so one technique that's emerging is what researchers call structured prediction. Instead of the model predicting every single pixel independently, it learns to predict higher-level structures like this object moves left, this shadow shifts, this color fades. That requires fewer computations than pixel-by-pixel generation, but the results can still look very natural.
So it's like the model is learning to think in terms of concepts rather than raw data.
Yes, exactly. And that's where neural architecture search comes in. Researchers are using AI to design more efficient model architectures. They're finding designs that maintain quality while reducing computational demand. It's a really active area of research right now.
So the trajectory here is, what? Are we going to see video generation become as accessible as image generation in a few years?
I think we'll see continued improvement, but I wouldn't expect it to become quite as accessible in the near term. Here's why. Video is fundamentally more complex. Even with perfect optimization, generating a 1-minute video is always going to be more demanding than generating a single image. That's just the nature of the problem.
But more accessible than it is now?
Oh, definitely. I think within the next couple of years, we'll see models that can run on 16 to 20 gigabyte GPUs and produce genuinely useful video content. And as GPU technology improves and prices drop, the bar for entry will keep lowering. We might even see mobile or edge device video generation eventually, though that's probably a ways off.
All right, we've got a caller on the line. Go ahead, you're on the air.
Yeah, this is Jim from Ohio. Look, I've been listening to you two geek out about compression and latent spaces and whatever, and I gotta tell you, you're way overthinking this. Back in my day, we didn't need all these fancy optimization techniques, we just worked with what we had. Also, it's been raining here for 3 days straight, and my gutters are getting clogged, which is completely unrelated, but I'm in a mood about it.
Sorry to hear about the gutters, Jim, but what do you mean we're overthinking it? This is pretty technical stuff.
Yeah, but the point is simple. Video generation is hard because video has more data. You want to run it on a smaller GPU, you either wait longer or accept lower quality. It's not rocket science. Why do we need all these papers about temporal distillation and whatever? Just make it smaller, make it slower, problem solved.
I appreciate the perspective, Jim, but I'd actually push back on that. The research into optimization techniques isn't just academic exercise. It's about finding the sweet spot where you don't have to sacrifice too much quality or speed. What you're describing, just shrinking the model and accepting lower quality, that's one approach, but it's not the most efficient approach.
Look, I don't buy all that. Seems like you're trying to make it sound more complicated than it is. My cat Whiskers understands simple cause and effect better than this. Anyway, thanks for taking my call, even if you're both full of it.
Thanks for calling in, Jim. We appreciate the feedback.
So circling back to the practical question, if someone listening to this has a consumer GPU with, say, 24 gigabytes of VRAM, what should they actually do?
Right. Let's talk real world. What's the actual path forward for someone who wants to experiment with video generation locally?
First, I'd recommend starting with frame interpolation. There are open source models specifically designed for this, things that can run on modest hardware. You can take videos you already have and enhance them, which is immediately useful. That gets you experience with the tools and the workflow without hitting a wall on compute.
What models are we talking about? Are there specific ones people should know about?
There are several. Rife is one that's been around for a while and is quite efficient. There are newer variants that are even better. These can run on 8 to 12 gigabytes easily. You get smooth, slow motion or frame rate enhancement, and it actually looks good.
And then once they get comfortable with that,
then they can move up to image to video. Models like Stable Video Diffusion, which came out in 2024, are designed to be more efficient than pure text-to-video models. You can run these on 24 gigabyte GPUs if you're using quantization and some optimization tricks.
Quantization? That's like compressing the model itself, right?
Exactly. You're representing the model's weights with lower precision numbers. Instead of full 32-bit floating point, you might use 16-bit or even 8-bit. You lose a tiny bit of precision, but the computational demand drops substantially. It's a very practical technique.
And this doesn't destroy quality?
Not significantly, no. With good implementations, the difference is barely perceptible. It's one of the best bang-for-buck optimizations available right now.
So if I'm hearing you right, the landscape is actually pretty encouraging. Like, yes, video generation is harder than image generation, but there are real practical ways to run it locally.
I'd say that's fair. It's not as plug and play as image generation yet, but it's absolutely doable for someone with the right hardware and a willingness to learn. And the trajectory is clearly toward easier, more accessible video generation over time.
What about the future? Like, 5 years from now, where do you think this is going?
Well, if current research trends continue, I think we'll see models that are specifically optimized for consumer hardware. Right now, most models are designed with cloud deployment in mind. But as local inference becomes more popular, we'll see more models built from the ground up to be efficient. That's a huge opportunity for improvement.
And then there's the hardware side, too. GPUs keep getting better and cheaper.
Right. The NVIDIA RTX 5090, or whatever the equivalent is in a few years, will be dramatically more powerful than current consumer GPUs. That's going to push the entire curve forward. What requires a data center GPU today might run on a consumer GPU in 3 or 4 years.
But we're also probably going to see more demanding models, right? Like, the frontier models will always push the limits.
Oh, absolutely. It's an arms race. As hardware improves, researchers push the boundaries of what they try to do. We'll probably always have a frontier of models that require serious hardware. But the mid-tier, the practical, useful models, those will become more accessible.
Okay, so practical takeaways for listeners. What should they actually do with this information?
First, if you're interested in video generation and you have a GPU, don't assume you can't run anything. Start with frame interpolation and see what's possible. You might be surprised. Second, if you're planning a GPU purchase, keep video generation in mind as a use case. It's becoming increasingly practical. And third, stay curious about the research. This field is moving really fast, and new techniques are being published constantly.
And for people who don't have a GPU, should they just wait?
Not necessarily. You can still experiment with cloud-based solutions to understand the capabilities and limitations. And honestly, if you're just curious about what's possible, those cloud services are quite affordable for casual use. You don't need to invest in hardware to get started.
I think one thing that strikes me about this whole conversation is that video generation really highlights how different AI modalities have different challenges. Like, image generation hit mainstream pretty quickly, but video is proving to be this much thornier problem.
Yeah, and I think that's actually valuable context for how we think about AI development in general. Not all problems are equally solvable with the same approaches. Video requires different thinking, different optimization strategies, different hardware considerations. It's a reminder that AI isn't just one thing, it's many different things, each with its own challenges.
And that's why prompts like this one are so useful. Because it's not just about what's possible, it's about understanding why certain things are hard and what we might do about it.
Exactly. And I think for people who are interested in the technical side of AI, video generation is honestly one of the most interesting frontiers right now because it forces you to think about all these optimization questions. It's not as flashy as text to image, but it's where a lot of the real innovation is happening.
Alright, well, thanks to Daniel Rosehill for sending in this prompt. It's been a deep dive into some genuinely fascinating technical territory. And thanks to all of you listening out there. If you've got weird prompts of your own, technical questions, strange ideas, anything you want us to explore, you can always reach out and maybe we'll tackle it on a future episode.
You can find My Weird Prompts on Spotify and wherever you get your podcasts. New episodes every week.
This has been My Weird Prompts. I'm Korn, and this is Herman Poppleberry. Thanks for listening, and we'll see you next time. Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify, or visit myweirdprompts.com.